Okay, now we're going to calculate the electric potential based on point charges. And we can actually calculate the electric potential also based on line charges, area charges, and volume charges. Very similar to what we talked about very briefly with Coulomb's law. However, we're just going to take a look at point charges because, again, when you do line integrals, when you do integrals in 2 dimensions and 3 dimensions, it really gets quite complicated, and that's really the realm for computers to handle. So calculation of electric potential, we know that the electric potential is also related to the electric field. We've already talked about that. We're going to talk about that more in the section after this. But when we look at the electric potential based on the electric field, which we get from Coulomb's law, when we do this integration, we see that the electric potential goes by Ke, the electrostatic constant, times Q, the point charge that's creating the actual field, and the potential divided by R, which is the distance from the center of the charge. Now again, this is a very general form of electric potential based on the field, and we'll get into that more in the next section. But again, for a point charge, this really does simplify because, looking at the form for the electric field with this constant Ke that can go in front of the integral, we have a constant charge that can go in front of the integral. We're left with the integral of 1 over r squared, which gives us negative 1 over r, and that finally gives our final form right there. So this is what we're going to be sticking with most of the time. And in fact, whenever we're looking at calculating the potential, we can use the superposition principle and say that the total potential is actually going to be equal to the potential due to each individual charge. So just looking at the electric field versus the electric potential, we can see here that the electric field again goes by 1 over r squared, so it drops off very quickly. You double the distance and your electric field is down by a factor of 1/4. You triple the distance, your electric field is now down by 1/9. With the electric potential dropping off by 1 over r, it's a little bit different here. That means that if we double the distance, we're down to 1/2. If we triple the distance, we're down to 1/3 the potential value. So again, you can see that this 1 over r dependence is slightly different than what we have with the electric field. To visualize the electric potential around a charge, we've drawn these 2-dimensional graphs. Of course, when we're looking at the potential, it actually goes in 3 dimensions, and we can't express the potential as 1 dimension and then have all 3 dimensions included. So this is sort of a 2-dimensional plot of what the electric potential looks like, and we see that very close to a positive charge, it gets very great, close to the charge, and in fact, if the charge were infinitesimal, the electric potential would go to infinity. Surrounding a negative charge, the potential looks sort of like a pit right there, and again, we can imagine that if we place another positive charge near this, it would sort of roll down this little topography that we see here representing the electric potential. If we put a positive charge near here, it would be attracted very strongly to that negative potential right there. My clicker, took a little time. So once again, electric potential of multiple point charges. Instead of just writing the potential out due to 1 charge, we can write it out due to multiple charges, Q2, Q3. And since Ke is a constant that can actually go out in front, we're just taking the summation of each individual charge divided by the distance that we are from that charge. Now remember, each potential is going to be unique to a particular position. So, depending on the organization of the charge, we will get different values of R1, R2, R3, depending what the geometry is. So here's what a dipole might look like. Again, doing our 2-dimensional graph, where we're showing the elevation as being equal to the charge. We can see a positive charge and a negative charge. Of course, they've stop it right at right where it would go to infinity. And again, if we have more than one charge, we have to talk about the potential as being basically a summation of both contributions. So let's take a look at this charge Q1. Okay, it produces a potential at point P of V1. Okay, V1 is equal to KE Q1 divided by R, the distance to point P. So if I were to put a charge at that particular location, we can relate the electric potential from Q1, okay, to the potential energy between Q1 and Q2. It's very simple. If the potential, the electric potential goes by KEQ1 over R, simply by multiplying it by Q2, the amount of charge that we put at that location, we can get the electric potential energy. Remember, electric potential is how many joules, how much energy, how many joules of potential energy we have per coulomb. If we multiply that by the amount of charge, we get energy. So again, two charges, if they have the same sign, we know that there's a repulsive force between them, and what that means is that the potential energy is going to be positive. Okay? That means that if you release them, they're going to accelerate away from one another, and that energy that was potential energy is going to be converted into kinetic energy. If they're opposite side charges, then the system now becomes bound. Okay? The two charges can't escape one another without additional outside work. And in fact, if they're let go, they'll accelerate toward one another, converting even more potential energy into kinetic energy and becoming even more bound. It's a basic property of bound systems that the total potential energy must be negative. And what that means is, if we're going to free these particles from one another, free a system of objects from one another, we have to do work on the system to separate the charges. If the potential energy is positive, that means that they're unbound, and if released, they'll simply go away from one another. So in terms of solving different electric potential problems when we have point charges, once again, we're going to use this very basic equation where the potential is equal to the electrostatic constant times the charge divided by the distance between the point of interest and the charge. And if we have multiple charges, we're simply calculating using this equation over and over again. So superposition principle simply means that we have scalars here. We simply add the total potential of each individual contribution. Now, let's take a look at an actual problem. Here we have two charges right here, and we're interested in what the potential is at that point P. Remember, the potential is going to be different all around these two charges depending on the location. Okay? So if I want to calculate what the potential is at that particular location, I have to determine the two distances, R1 and R2. I know the charges. Okay, in this case I have 8 microcoulombs and negative 4 microcoulombs, and I add V1 and V2 for point P together, and I get my total potential. So in this particular problem, R1 was easy to determine. I just look at that graph and I see that, okay, our point of interest is 4 meters above the origin. Our first charge is located at the origin. And now for R2, I see R2 is slightly off to the side. It's 3 meters on the x-axis, it's 4 meters away on the y-axis. Of course, this gives you your classic 3, 4, 5 triangle. You can prove that to yourself, that R2 is 5 meters away. So I have my distances, and that's usually the first thing that I'm going to do when calculating the electric potential for this. Okay? Now, simply calculate V1 and V2. All right? Here's V1, here's V2. V1 is based on KE, Q1 over Q1 over R1. V2 is KE, Q2 over R2. Okay, I can actually put this KE out in front and add Q over R, Q over R. And you can see the rest of this is just, basic algebra. And I end up with the total electric potential of 12,000 volts at that particular location. So sort of remarkable, such a small charge, here we're talking about microcoulombs of charge, are producing such a large potential. But again, we've got to remember that this constant right here, the electrostatic constant, Ke is 9 times 10 to the 9. It's a really large number. So even for a moderate distance, a couple meters, and a fairly small charge, I'm going to get a large value for my electric potential.